Okay, so go ahead and open up Excel.
There a worksheet for this one?
There is no worksheet, just a blank worksheet. Okay. So what we're going to do, well, maybe I should write a couple things. All right, we're going to talk about chapter 8.1. Am I sharing this? I'm not sharing this. Share. Okay. So we're going to talk about chapter 8.1, which is distribution of the sample mean. Okay? And we're going to talk about one of the most important theorems in all of statistics, which is called the central limit theorem. Okay? And the central limit theorem basically says that regardless of the underlying distribution, X bar becomes approximately normal as the sample size increases. Okay? What this means is that quite often the normal distribution can be used even if the underlying population is not normal. Okay? Which is really super powerful. So I just want to highlight this central limit theorem, super cool theorem. Okay? Now, it says as the sample size increases. Okay? Now, we talked, I guess I gave you a preview of this because I was so ready for it to talk about. I gave you a preview of this yesterday, just as a reminder here, how big is big enough. You guys remember what we said yesterday? I really was supposed to teach that to you today, but I taught it to you yesterday. Okay, so you go ahead. Oh, you want me to zoom in a bit? Okay, so Trevin said one of the rules, and say it a little louder. NPQ must be greater than or equal to 10, and that's for what kind of data? So it's discrete, really, I probably should be more specific. Really, it's binomial data. Okay, but binomial is discrete. Okay? And then, what was the other rule? N is greater than or equal to 30, and that's for continuous data. Maybe I'll move this over here. Okay. All right. So now remember, and I'm going to put this in all caps, this is not a magic number. Okay. So 30 isn't like you get out of jail free card. It's automatically. Nothing's automatic. Okay. You still need to do histograms. You still need to do QQ plots. But if it works a lot of the time, it works most of the time. Okay. All right. But yeah. All right. So now here's what I'd like to do. Let's open up a new spreadsheet. I probably should have written that on the board, but you probably read it better when it was on the computer, right? Okay. So actually, here's what I'm going to do. I'll write this here, and then I want a blank page. Okay. So we're going to do an example. The Stanford Binet IQ test is normally distributed with a mean of 100 and standard deviation of 15. Okay, we're going to do a simulation of 900 random students using the uniform distribution. Okay? All right, so we're going to do that on the next page. And the reason I didn't want to write that on the next page is it just makes my life a little easier. Okay, so here's what we're going to do. I'm going to just do some random numbers, ran between 75 and 125. Okay? Now I'm going to copy this over. I'm going to go over 9 columns. So 1, 2, 3, 4, 5, 6, 7, 8, 9.
75 and what?
75 and 125. Okay? All right, so we're doing a simulation to simulate that. And then we're going to go down 100 rows exactly. Okay, 100 rows. Okay, so these are a bunch of numbers here. Notice when I type, the numbers change. I want that not to happen anymore. So I'm going to highlight all these columns. I'm going to right click. I'm going to say copy. I'm going to right click again. I'm going to paste special 1, 2, 3. So now when I type, these numbers don't change anymore. So you'll have different numbers, but it should work just as well for you. Okay, what'd you say? Do what again? Okay, so highlight all the columns. You're going to right click. You're going to say copy. And then you're going to right click again and you're going to click on the 1, 2, 3. So now you don't have that ran between thing. These are just whatever these numbers are. Okay? All right, so let's pretend, I'm going to insert a row here. We're going to pretend this is a population of 900 students. Okay? Now, how would you find the population mean? No, I don't want to highlight everything just yet. Equals mean. There's no mean command, dang it, because Bill Gates is mean.
Yes.
Average, curse him, curse Bill Gates. We love all the software, but curse him for not putting mean there. Now you highlight all your data. Okay? Now remember, with our example, we wanted our mean to be 100. Let's see how close we get here. Okay? 99.34, that's pretty good. Okay? Let's do the population standard deviation. How do I do that? What?
A lot of numbers be different, by the way.
Your numbers will be different, but it should be close. Standard deviation, which one do I pick?
The one
With the P, the population. Okay, standard deviation of the population, I'm going to highlight all my data. Okay, now we wanted it to be about 15, 14.7, not bad. Okay, so these numbers are pretty close. Okay, so these are very close to what we wanted to do. Now, I'm going to do something I told you guys never to do, but I got 900 students here, and I also want to prove a point. Okay, I'm going to use the histogram maker. I've never done this before. Hopefully it's okay. You guys are my witnesses here. Histogram maker. Okay. I don't like this histogram maker, but anyway, at any rate, does that look normally distributed to you? No. Is my, well, I'm going to call this a sample size, but this is really a population. Is it larger than 30?
Yes.
Yes. Okay. But this would be, I think because, see, this is why I don't like the histogram maker, because it really should have stopped at 125. And I think that if it did, if we'd have done this ourselves, these would have all been, this column would not be smaller than the others. This is one of the, another reason why I don't like that. But anyway, it should be a big rectangle because it's a what kind of a distribution? It's uniform. These are random numbers. So a lot bigger than 30, it's not normal. Okay? So just want to make that clear. And I think, yeah, like I said, If these were equally sized, this one probably would be taller than it is here. All right. Oh, go away. I want the whole thing to go away. All right. So we know that this is a uniform. The population is a uniform distribution. Okay. All right. So what if I'm going to treat every row of 9 people, and I want to find the sample mean. Okay. I want to treat them as a simple random sample. Okay. These are just random numbers, right? So I'm going to find the mean of just the first row. Okay. So the first mean I get is 103. I'm going to do this for all 100 rows. So I'm going to copy this down. Okay, so as you can see here, we've got some variation. Oh, look at that. So I got 100. That was like almost around 108, 93. So there's some variation going on here, right? Okay. Now, according to the central limit theorem, this is what I want to emphasize. According to a central limit theorem, if I did a histogram of the sample means, what should it look like? Okay, so let's review what does the central limit theorem tell us. Central limit theorem says regardless of the underlying distribution, which in this case is a uniform distribution, these are just a bunch of random numbers, X bar, that column I just highlighted, becomes approximately normal as the sample size increases. So I'm going to ask that question again. When I make a histogram out of this, what should it look like? It should look normal. Do you think it's going to look normal? You believe it? Okay, we're going to find out. I've never done this in class before. Oh, look at that. Does that look pretty normal to you? A lot better than the underlying distribution. Okay? So that's a perfect example of, and in fact, if I'd have done my own things, it probably would have even looked better than this stupid automatic one. But yes, that's pretty good, right? That looks roughly normal, okay? So that's the central limit theorem in action. Now, not only that, but here's what's cool about this, okay? Now, let me ask you a question. So I did the mean of each row. What if I did the mean of my means? Okay, so I'm going to find the mean of this column. Now, don't press enter yet. I want you to guess here. Okay, so don't give away the answer before I press enter. My question to you is: we know that the population mean in my case is 99.34. Okay, do you think the mean of the means will be the same as 99.34, or will it be slightly different? Who thinks it will be the same? 1, 2, 3, 4, 5, 6. Who thinks it will be different? 1, 2, 3, 4, 5, 6, 7. Okay, it looks like, okay, so I have a half. Didn't raise your hand. You got it wrong. Okay? All right, so drum roll, please. What happened? Oh, man.
Close your parentheses.
No, I didn't. I said it over time. I just needed more suspense. 99.34. How about that? Okay. So that's really cool because what it means here, I'll add this to the central limit theorem. Slide this down just a little bit. Is what's that? It shouldn't have. It should have come out exactly the same. If it did come out different, you did something wrong. Okay. But what it means is X bar is an unbiased estimator of the population mean mu. Yeah, yours should have come out exactly whatever your population mean was. Okay? Which is really super cool. Unbiased means you nailed it. Okay? And in our case, I got my sample mean, or my population mean matches the mean of my means. Okay? So that's really awesome. That means you can trust X bar to be a very good, now notice there's going to be some variation here. But what we're saying here is that the mean of your means, X bar, is going to be a very good estimator of the population mean, okay, an unbiased estimator. All right, so now we know that the population standard deviation is 14.7. What if I did the standard deviation of my means? Okay, now before we press enter, I'm going to ask you a question. If I do the standard deviation, now these are samples, so I'm going to use my sample this time, of this column here. Before I press enter, I'm going to ask that question again. Do you think my standard deviation will be the same or will it be different? Okay, who says it's going to be the same? 1, 2, 3, 4, 5. Who says it's going to be different? 1, 2, 3, 4, 5, 6, 7. Did you raise your hand twice? No? Actually, I think we got 8. Okay, so we got 8 people that think it's going to be different, 7 people that's going to think it's going to be the same. So here we go, drum roll, please. Oh, it's different. It's very different. Okay? Okay, so it's actually quite different. Okay? Now, what is the relationship? Okay, so the relationship between this is, okay, so X bar is an unbiased estimator of the population mean. However, your standard deviation is biased, okay? And it's biased much lower than the population standard deviation, okay? So we refer to the standard deviation of X bar is called the standard error of the mean. Can I underline that? I want to see if I can. And matter of fact, maybe I'll write this on the board because I don't want to write that there. Okay. So here, I'll stop sharing for a moment. Okay. So when we're talking, so X bar is unbiased estimator of population mean mu. Okay. And the standard error of the mean, okay, is going to be this. So the standard deviation of X bar equals the standard deviation of the population divided by the square root of n. Okay? So that's the relationship. So here's what I mean by that. Oh, I didn't get that on camera. There we go. It's now on camera. Okay, for those of you who are watching at home, why aren't you in class? Unless you guys are all rewatching it, that's fine. All right, so here's what we mean by that. Share my screen again. Okay, so here's what we mean. So if I take the population standard deviation, which is 14.7, now how big was my sample size for each row? It was 9, right? So I'm going to divide that by the square root of, in this case, 9, okay? And what I'm telling you is it's going to come very close to 5.3, 4.9. Okay, so it's off a little bit. But what we do is this here becomes an unbiased estimator of the standard deviation of the sample mean. Okay. For those of you who are watching at home and you want to see that, I'll stop sharing so you can see what I wrote on the board there. But yes, so that's the relationship. Okay. So now here's the deal. I'm going to introduce to you a new equation that I normally introduce a little sooner, but we'll see if it confuses you. Yes?
So how far off is considered bad when you do that? Because mine was 0.65 off.
It's good enough. Okay, yeah, so this is going to be our relationship. So you remember previously, okay, so previously the formula that I gave you was z equals x minus mu over sigma over the square root. No, that's what I gave you. That was the formula I gave you before. The The formula I'm going to give you today concerning this is a very similar formula. And it's going to be Z equals X bar minus mu over sigma over the square root of n. Okay? So you can see those are very, very similar formulas. Now here's how I'm going to tell you to remember them. Okay? This is the formula that I would prefer that you use all the time. Okay? And here's the deal. If your n is 1, okay, what's the square root of 1? 1. So this just falls out, and it becomes this equation here, right? Okay? So this is the better formula to use. Because if your n is 1, you got that back. Okay? So when you're doing problems, and you're trying to decide, do I use this one or this one, I'm just saying just use this one all the time. Okay? And here's how you do it. If there is a sample size listed, use this one. If there is not a sample size listed, assume that your sample size is 1, and then it becomes that equation anyway. So you're safe. Okay? So this is definitely the better one to use. Okay? So if you get confused, use this one. Okay? Now the difference is this is an X bar, this is an X, so that's the other difference. But to me, it's easier just to look and say, is there an and in my problem? If there is, use it. If there's not, use it. You know, it becomes the same equation. Okay? Does that make sense? Okay? All right, so let's do an example here. All right, so let me share another screen here. Share. Okay, so I'm going to open up a third tab here. And let's say that the mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. 12.9. Okay. Weight gain during pregnancy is skewed right. An obstetrician in a low income neighborhood, oh my gosh, I can't type, obtains a simple random sample of 35 and determines the mean weight gain was 36.2 pounds. Should she be concerned? Okay. Now, I want to emphasize a couple things. Let me back up here. I forgot to mention one other thing back here. Now, remember, we said here, how big is big enough? N should be greater than or equal to 30. My N for each of these rows was only 9. So you can actually get away with smaller things. Now, what should I have done in order to use a smaller than 30 sample size? We had a quiz on it today. What'd you say? What do you use when you have a small sample size? What'd you say? You guys all had a quiz on it today. You've already forgot. You can't even remember for 45 minutes. QQ plot, right? Now, technically, I should have done a QQ plot, but I'm in a hurry and I've only got 5 minutes left. I want to do one more problem. But yes, I should have done a QQ plot. So yes, you can get away with smaller sample sizes. Sometimes the central limit theorem works with even smaller than 30. I really should have done a QQ plot, but I've done this so many times it didn't work. Okay? All right. Now, let's also talk about this. Weight gain during pregnancy is skewed right. Is that an issue? Who says yes, it's an issue? 1, 2, 3, 4. Who says no, it's not an issue? 1, 2, 3, 4. You didn't raise your hand. All right, so let's talk about this for a second. So according to the central limit theorem, okay, I'll just leave that there. So let's say, so skewed right would mean that it would look like this, right? This is the population. Okay, and let's say it says that the mean would be about 30 pounds. Okay, and according to the central limit theorem, I've got a sample size of what according to this problem?
It's less than 35.
35. Okay, and it's so basically what the central limit theorem says, regardless of the underlying distribution, I'm going to get a nice normal distribution. It's going to be, in this case, it was 36.2 pounds. I think it said 36.2. So this is going to be my X bar. This is going to be my mu. Okay. So what it's saying here, the central limit theorem says, regardless of the underlying population being skewed, I still think when I do my random sample, it's going to be normally distributed. Okay. But they didn't give us any data, so we can't actually do a QQ plot. But we're going to make that assumption because the central limit theorem says we can make that assumption. Okay, and theoretically my sample size is large enough, and they didn't give me any raw data, so I can't do a QQ plot. So, but we're going to make that assumption as being true. Okay, all right. So this is what's going on now. The question is, should she be concerned? What does that mean exactly? Should she be concerned? Yeah. Does it look like? Because it looks like her patients are gaining more weight than the average woman, right? Should she be concerned that her patients are gaining more weight? Okay, so what we're going to say is, if the probability that her patients gain 36.2 pounds, given that the normal is 30 pounds, if that is less than 5% of the time, we're going to call that, we will call that unusual. Okay, so if we get a value that's less than 5% of the time, then we're going to say, yeah, it seems like those are farther apart than they should be. And that seems unusual. It seems like something's going on with this low-income neighborhood that's causing women to gain more weight than they should. Does that make sense? So I'm going to give you this is kind of a general rule. If something happens less than 5% of the time, we're going to say that's unusual. Okay? So how do we find out if this is unusual? Z-score. My favorite equation right here. Sorry, those of you who are watching at home, this equation here. Okay, so here's what we're going to do. We're going to do our Z-score. Z equals X bar minus mu over sigma over the square root of n. Okay, so let's pick on Tyler. Can you help me type this up? Okay, in fact, maybe one of the good things to do here is to go through and, in fact, this is a really good idea. Go through and explain what all these numbers are. So this first number here, we got something equals 30. What equals 30? The mean, which mean? Mu. We're calling that the population mean. Okay. Something equals 12.9. What is the 12.9? Which standard deviation? That's why these questions are hard. You really should identify these. This is a really good practice. Just go through, identify the numbers. So it is a standard deviation, but which one is it? Does it relate to the population? Does it relate to the sample? This is the population standard deviation, which is going to be the letter sigma, right? Okay. Weight gain is skewed right. So she turns it's a random sample of 35. What's 35? That's your sample size, and we represent that by letter M. Okay. Determines the mean weight gain is 36.2 pounds. What's 36.2 pounds? X bar, because that comes from your sample, right? Okay, so we've identified everything in here. Now help me punch it through. X bar is 36.2 minus 30. That's my numerator. And my denominator is 12.9 divided by the square root of 35. I'll put a little underline there so you can know that. So this is going to be the numerator divided by my denominator. That works out to be 2.84. What is 2.84? That's my z-score. Okay. So essentially what we're doing, okay, and now the idea here is, let me go back to my picture for just a minute. Okay, we're trying to find the area of the tail here, this area here. Okay. So now, how big is that? How do we find that with the computer? Okay, norm S dis, is that going to give me the red or is that going to give me the white?
1 minus.
We need to do 1 minus, right? Because it's going to give me the norm S dis is going to give me the white. Okay. So as I'm doing this, okay, I'm going to refer to this as my p-value. My p-value equals 1 minus norm S dist of this value here. And we're saying, wow. So I kind of exaggerated here. We're saying this is 0.00223. Okay. Does that seem unusual to you? Yeah. So what we're saying is that happens 0.2% of the time. Okay. Given that the mean weight is 30 pounds, the fact that her patients gain 36, that happens 0.2% of the time. That's highly unusual. Yes, this is strong evidence that for whatever reason, her patients are gaining 6 more pounds than they should.
How do you get the p-value?
1 minus norm S dist. Yeah. Okay. All right. So quiz tomorrow is on 8.1. So you're going to be focusing mainly on this equation here. So see y'all tomorrow.